Okay, now that we know what a quadratic equation is, we want to be able to, in this next section, talk more about a quadratic, an absolute value, and square roots, and typically talk about their graphs as well. So solving quadratic equations, applying the definition of absolute value, using quadratic equations to solve area problems, and graphing the different functions as well. So let's get started on those objectives. If we're going to explore quadratic functions, remember, they are, as we've seen before, just parabolas. So if we asked you to graph this, y equals x squared minus 3, and you can have your graphing calculator out ready to go, you should be putting in values. If you're doing it by hand, that would be positive, negative, and zeros, because we know what happens there. If you're going to your calculator, go ahead and do that. But you should have an XY table with some positives, some negatives, and zero. And if not, you're just using your calculator, you should be able to look at those values on your table. So in doing that, we have y equals x squared minus 3, which is standard form. It just has one of the terms missing. So if you think of it as our y equals ax squared plus bx plus c, so something we've done in the past, we really have an ax squared term, and our a value is actually 1. We do not have a bx term, so that means b had to have been 0. And we have a c term, which is the negative 3. Okay, so either by hand or with your calculator. Hopefully I've given you enough time to graph. Let's see, hopefully, what you came up with. Now the only thing is I did not connect mine, which your calculator would have done. But these are some of the values. So 0, negative 3, 1, negative 2, negative 1, negative 2. Okay, so you're seeing these points listed. And you can make some observations, some inferences. So what did I say? I said negative 1, negative 2. And I said positive 1, negative 2. Positive 2 was a 1. Negative 2 was a 1. And even if we went further, if we went 3, it looks like 6. And negative 3, negative 3, positive 6. So you're seeing that symmetrical look that we've talked about in the past, that symmetry related to this. So here are some things we want to just revisit as we explore quadratic functions. Graphing quadratic functions of the form y equals ax squared. Now obviously that's the easiest form. We're missing that bx term and that c, it means there's 0. So it's the shortest compacted form of a quadratic we can have. We definitely want to talk about the phrase of parabolas, and we hopefully know that that's the shape of the graph of all quadratics. The axis of symmetry, where that line cuts your parabola in half exactly, so this would be the line of symmetry. Standard form we've already discussed in the previous section. The vertex of a parabola really should only be 1. The vertex is that higher low point, which is then referred to as the minimum value, the maximum value, the min point, the max point. So in this example, I would have a minimum point. The lowest point here is where that point is or has the lowest y value on our graph. All right, so when we talk about axis of symmetry, most of us have been exposed to this through our geometry class, but let's look. Axis of symmetry. The line about which you reflect a parabola or any other shape onto itself. So, question is, can you draw a line of symmetry through each of these objects? If so, write the maximum number you can draw. Or think about it in this case. So right now, go through, and we've got the rectangle, the triangle, the red rectangle, the domino over there, the hexagons, the protractor, the trapezoid, irregular trapezoid. So think about all those different looks and what happens on each of them in regards to symmetry. We know a parabola, which we've just been talking about, really has a line of symmetry. And it is that place where you can cut your parabola in half exactly. So knowing that, that's what you're looking for on these shapes. So if you would, we're going to have Mr. X-ray Vision Man come and divulge our answers. So everybody, let's start up here with the domino. We'll go across or up and down. We'll just go to it. So X-ray Vision Man is going to say how many lines of symmetry you see in the domino, and you should have your answer already. So if you do, it's 1. And notice where it's drawn. It cannot be 2 because of where the dots on the domino were at. All right. The next one, our triangle. There they are. There's 3. Our other rectangle over here, there are 2. Some people think there's 3 on a rectangle, but if you fold on corner to corner, it does not match up exactly. Just try, for example, a 8.5 by 11 notebook piece of paper that you might have. It does not match exactly, and they have to match exactly. All right, down here on our irregular shaped trapezoid, none. Look at that shape again. You cannot fold over and get matched exactly. What about the protractor? 0 also, and the reason for 0 is because there's numbers on it, just like the dots on the domino. You cannot get them or they do not match up. Look at them again. So 100 on the right side should say 100 on the left also, and that top row, and it doesn't. And last but not least, our hexagon. Whoa, we got a bunch there. Did you get all of them is the question. There are 6 of them, and they are brightly colored to show you those. So make sure you realize not everything just has one line of symmetry. You got to take different perspectives for different shapes. But parabolas, we're going to stick with, at this case, they have one line of symmetry. All right, so let's review. What is standard form for a linear equation? Notice I said linear. That was last chapter, last semester. And you should be saying what? AX plus BY equals C. Good job. Standard form, next question. What is standard form of a quadratic? I should have asked the question before I divulged it. And then if you look at both of those, the question is, what do you notice both have in common? A couple things you could say. Some of you might say, well, they both have the variable x and y. They do. They both use the letters A, B, and C, even though they do not mean the same thing in both. One of them is solved for y, the other one is not. But they said, what do they have in common? So looking at them, those are just some commonalities and differences as well. All right, make a table of values and graph the quadratic function. So I'm saying we've got y equals 2x squared and y equals the opposite of 2x squared. So I want you to do a little discovery here this time. On your calculator, you guys do that. And when you do, you should be able to get some negative, some positive values. So I'm just going to go with my x values here. Now, if you've got it graphed, let's see if your results show. Now, you should know right away this is a parabola through 0, 0. Sorry. And we're getting some points. When x was -3, y was 18 on the one, it was -18 on the other. -2, -2. -1, -2. 0, 0. 1, 2, 1, -2. So you're seeing the exact same values, except for now opposite signs. So when you graph that, if we started at 0, 0, we'll go in green first. Green. That's better. -1, 2. +1, 2. We go one more. 2, 8. And -2, 8. And we could draw with a smooth curve our parabola, putting arrows on the end. And then we'd go red on the other, and we would have the same combination here in the middle, 0, 0. Then we'd have a 1, -2, a -1, -2, a 2, -8, and a -2, -8. Again, with a smooth curve as possible, cutting through those points and drawing your arrows on the end. What we're seeing here is they're the identical parabola in terms of width, how wide you are between the two branches. They both share the origin as its vertex point. One is a minimum point, one is a maximum point. But if you look back at your two original equations up here, what's the only difference you're seeing? That negative sign. That negative sign out front made one go up and one go down. So that is our A value determines the direction. If A is, we'll say here, if A equals a positive number, we know our parabola is going up. If A equals a negative number, our parabola will be facing down. And that is guaranteed every single time. So it's telling you something about your parabola before you even start. All right, here we go. Can you figure out how many parabolas were used in the figure below? So we got our smiley guy there. How many have positive A values? Based on that discovery we just made, how many would you say have positive A values? 2, 5, 7, or 9? And you'll have your answer. Positive A values, 1, 2, 3, 4, 5 of them. They always have parabolas that open up. Next question. How many have negative A values? Well, if 5 of them had positive, what does that leave? So going back to your work, a negative A value always goes down. There were only 2 downward parabolas in that smiley guy. So which parabolas have maximum values? Think about what that means. Maximums, a negative A value always goes downward, which means they also have maximum values. The highest point means max. And the last one then gives you which parabolas have minimum values. Is it 2, 5, 7, or 9? Again, anything that has a minimum value had to have been an upward parabola. All upward parabolas, we counted, there were 5 of them. They also are the ones with the minimum value. Okay, so now we know a little more about our parabolas. Now, if this one it says graph y equals -4x squared, y equals 1/4 x squared, and y equals x squared, you can graph each of those fairly quickly, whether it's with your calculator or by hand. Go ahead and get started and see what you get. We're going to make some observations about them. We'll just put in a few positive negatives. That's all you have to do. Positive, negatives, and zeros to start getting where we're at. So this first one, y equals -4x. We know it's a parabola that goes down. We know it goes through 0, 0. Let's get our pen tool out. 0, 0. If we put a 1 in, we get -4. If we put a -1 in, we get -4. And that's about as wide as we're going to be able to graph on here. We put a 2 in and it's even going bigger. All right, so there's the first one. 1/4 x squared starts out at 0, 0. We put a 1 in, we get 1/4. So not going to be able to go up very high. We put a -1 in, we also get 1/4. If we put a 2 in, 2 squared is 4. 4 times 1/4 is 1. And we put a -2 in, same thing. Okay, so this time we have a much wider bowl-looking parabola. Okay, and last but not least, y equals x squared. We know it goes through 0, 0. Whoops, let's go a different color here. 0, 0, and then we put a 1 in, we get a 1. Put a 2 in, we get a 4. We put a negative 1 in, we get a 1. We put a negative 2 in, we get a 4 also. So here is the parabola on that side. And again, just drawing by hand. So you have all three of them drawn either on your calculator or by hand. And it says compare the widths of the graphs. You should be able to tell me something about what we just learned. We knew every single one of them went through the origin. 0, 0 was on all of them. We knew the first one went down. That was the A value we learned about already. We knew the second one went up. We know the third one went up. But now we should be able to know more about what happened with the widths. So start looking. Here's our skinniest one. Look back at our equation. Whoops, that was not good. It is definitely the red one. So here we go. And then the blue with the blue graph, and the light blue with the light blue. So look at them carefully. What are you going to be able to say? They only have an A value. And I think most people would say, oh yeah, the bigger A value. Now that does not include the negative in this case, because we already said the negative sign determines that it goes up or down. So we already know the negative sign made it go down. But now look, my 4 was the biggest number up there. 4, 1/4, and 1. 4, the skinniest one, the width is the skinniest, is there. The 1/4 is the smallest number, and it is the widest. And then we've got to 1. So I believe we're saying here the discovery we want you to make is that the bigger the absolute value of the A is, the wider, the skinnier the parabola is. It shoots up, it gets tighter to the y-axis. So right now we don't have much distance between here and here. Here it was 1/4, we have a much greater distance. Here it was 1, it's right between the two. So the width of the parabola, the width between the two branches. Okay, good choice. All right, so now, what effect does increasing the A value in the standard equation have on the graph? Now look, you can vote if you have voters. Otherwise, if A is positive, the parabola opens up and is wider. If A is positive, the parabola opens downward. If A is negative, the parabola opens upward. And then D is the choice, none of the above. Now, based on what we just observed, you should be saying D, because as A increased, the bigger the A value. The last one we did was 1/4. Just go back and look. The bigger number, 4. If the A value got bigger, it made this skinnier, not wider, which is the choice I think some of you wanted to make. If A was positive, the parabola opens up and is wider. It's not wider, it's skinnier. Okay, so D should be our choice. And this one's just if A is positive, the parabola opens downward. No way, that's bad. If A is negative, the parabola opens upward. Bad. So none of the above should be your answer. So another observation. Good job. All right, now we're going to switch to absolute values. Similar idea. You know the absolute value of different things already. So let's go and let's make this a black. So here we go. Let's start at the beginning. The absolute value of 0 is 0. The absolute value of 2 is 2. The absolute value of 4 is 4. The absolute value of 6 is 6. Absolute value of negative 2, 2. Negative 4 is 4. Negative 6 is 6. What is the definition of absolute value? Hopefully that you're working from. It should be that your distance from 0 is positive. A number's distance from 0, and distance is always positive. So what I got left here? 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then if we did the same thing over here, there's 2. 4, and here's 6. And if we drew this, it is not a curve like we had in the past. These are straight lines. It'll continue. The next thing would be 8, 8 over here. and we are getting a V effect on our graph. So using the absolute value function, determine the range. The range is our y value, our outcome, our f of x. So that's our range. And what are we getting? We're getting positive real numbers. And 0, because 0 is not considered positive. Plot and connect the points on the graph. We did. What just shape does it make? It was a V. The domain I didn't talk about actually on number 1. We can put any kind of numbers we want in here. So that's all reals. That would be the domain. Number 5, this type of function is called an absolute value. How can you associate the name of the function with the shape? Hopefully, right here. Absolute value graphs into a V. That's what we want. Given the graph you drew, name 4 other coordinate points on the graph. Now, you could keep going up with whole numbers, or we could just do some of the nice and easy ones. We did evens here. Let's just go with 1. If I go 1, what should it be? 1. What's the absolute value of 1? If I go negative 1, what should it be? Positive 1. 3, 3, negative 3, 3. You could go fractions. 1/2. Absolute value of 1/2 is 1/2. If you extended both lines, what is the domain and range? Use interval notation, meaning what kind of numbers are you going to get? If you want to say, all reals, you can. I don't know about interval notation. If we used interval notation, then we have to. So right now, if we said the domain, are x values that are what? Well, they can be positive, they can be negative, they can be fractions, they can be whole numbers. I think most people would say, well, then it needs to go from what we would say negative infinity all the way up to is greater than or equal to positive infinity. So x can be less than or equal to negative infinity. It can be greater than or equal to positive infinity. If we did the range, that one's going to be a little tougher because what are you getting? You're getting all non-negative reals. And I don't know if we're going to use an interval for that. Non-negative reals. So that would be positives and 0 if you like that better. Okay, so a V, big difference. It is not a smooth curve like we saw the parabolas. Now, you can go to your grapher, some of you have never done this before, and get an absolute value function. So follow this. Push your y equals like you're going to graph. Choose your first choice, y sub 1. Go to your math key. There is a choice of number 1. It's called ABS with a parenthesis. That stands for absolute value. Push enter. It now shows up on the screen. If you just want to do the equation y equals the absolute value of x, which is the basic simplest one that we're looking at, then you are then going to type your x value, and you will close it with a parenthesis. And I know that doesn't seem right because it says straight bar, but you opened it with a parenthesis in the notation. You have to close it with the same thing. So we do have the ABS function. You can hit graph, and it will graph just like this into a nice V on your calculator. If you've never done that before, that's how you would do it to get away with doing your absolute values by hand. Okay? Now, let's just refresh. So what that means is, when we did this, that we have an absolute value function, and we said the absolute value is going to be equal to x when you're dealing with positive values. So when you put in a number, what you put in comes out. However, here, when x is less than 0, that means when we put in a negative number, what we put in comes out as the opposite of what we put in. So what that means is, if I put in a negative 3, and I take the absolute value of negative 3, that negative 3 results in an answer of 3. So I got the opposite of what I had put in for x. So domain and range, and we did that on the last chart. The domain should be all reals, but the range should be non-negative reals. Only positive values for an absolute value. Now, this is a little different, and you are going to do a couple of these. What if they just say solve an absolute value? So now I want you to think, well, wait a minute. If they told me to solve this one, and I'm going to do this, to make it easier to start with, if I just say, whatever's underneath that, if it's a variable or whatever, you could think of it that way. You could think of it as x right now. Let's just do that for thinking purposes. If that's x and it says, what's the absolute value of x? And they say, if the absolute value of x equals 12, which is what this one does, then your question is, what's x? Well, the answer would be 12 is and negative 12 is. Because what numbers would go in here, would go into the black space that would equal an absolute value of 12? And we said from our result that basically we know if this is my 0, what numbers are equally spaced from 0 that come out to be 12? And we know 12 is, and we know negative 12 is. So we should get 2 answers on that one. Okay, now, if we did that with regular, nice, easy numbers, what's going to happen when it's a expression, not just one thing? You're going to have to solve it that same way, that same thinking. But we're going to have to write it slightly differently. So that's what we're headed to now. So whatever's underneath that spot, however complicated it is or easy it is, could be equal to 0. Could be equal to 0. Could be equal to 12 is our goal in this case. All right, so just revealing, so you can see where I'm getting what I have now. So whatever's underneath my inside of the absolute values might be a bit better way to say it. The 34 minus the 2y could be equal to the 12. As we also learned, what's underneath there, or what's inside the absolute value bar, could also be equal to negative 12, because we have 2 numbers. 12 or negative 12 is going to make that true. So that is basically, essence, what you have to do. You have to take whatever's underneath there, whatever's inside of the absolute value bar, and set it equal to the 2 possible things it could be, and work it out. So that's what our work is now. So here we go. We will subtract 34 from this side, subtract 34 from this side. Negative 2y equals a negative 22. Divide by negative 2, and y equals 11. It's one of our solutions. Other side, subtract 34 from both sides. We would get a negative 2y equals negative 46. We divide by that negative 2, and y equals 23. So what that means is you should be able to put an 11 back into the original and a 23 back into the original and get the absolute value to come out equal to 12. So let's just check it. If y equals 11, 34 minus 2 times 11, well, 2 times 11 is 22. 34 take away 22 is 12. The absolute value of 12 is 12. Next one, we put a 23 in. 34 minus, down here, 34 minus 2 times 23. Well, 2 times 23 is 46. 34 subtract 36 is a negative 12. But it says, what's the absolute value? Negative 12 is 12. So it checks. So you get 2 solutions for this absolute value. All right. What is a radical? A radical is nothing more than a fancy name for a square root. You've been doing the square root of 25. We like to call that radical 25 also. So what does it mean to simplify a radical? Well, you've done some already. If I said x squared equals 50, and you know that you could put a positive number in there, you could put a negative number in there. If it makes it true, then those are the solutions we're looking for. But most people will say, well, we do this just like we do algebra. So I want to get x by itself. To get x by itself, I need to undo the square. So undoing the square means I need to take the square root of both sides. That's the opposite of a square. When I do that, I get x equals, and I get 2 solutions here because there are 2 ways you can square something and get a positive answer. Positive times a positive, and a negative times a negative. So right now I'd be looking at the square root of 50, or plus and minus the square root of 50. But that's not the big thing we're worried about right now. It says, how do you simplify a radical? All right? Simplify a radical means break it down. So in other words, up here, we were taking the square root of 25 and breaking it down and saying it's 5. So you were taking the perfect square number out of the 25, and in that case, that's all that was left. We want you to do the same thing here. We want you to take the square root of 50. You're going to say, well, I can't. Well, you can take a perfect square number out, but there's other stuff remaining. That's the problem. So here we go. We're going to be thinking of this 50 as two other numbers. The biggest perfect square root number, so that would be 25 in 50. 25 times 2. 25 times 2 still gives me my 50, so it still goes up in checks. But now I can start saying, well, wait a minute. The square root of 25 is the whole number 5, and the square root of 2 is not a nice number, so we leave it as 5 root 2. And again, it would go back to plus and minus because there were two answers to begin with. So simplifying the square root of 50 would give us plus or minus 5 root 2. Just a reminder down here, when you do have a positive number for x, you get back to what you started with. When you have a 0, you get 0. And when you have a negative number, you get the opposite. Okay, so we're just saying basically you get two solutions here when you have something other than 0. All right, so there will be a few more right here that you can simplify. So with me, you're starting to think. And if you're not good at your perfect square numbers, this would be a situation where you might want to write them out on the side of your paper. So if we did that, 1 times 1, 2 times 2, 3 times 3, 4 times 4, 5 times 5, 6 times 6, and you can keep going as far as you need. And those are your perfect square numbers. Now, those are the only numbers that can reduce, break down a radical. So in this case, we're trying to say, what could we use? What times what is 45? There's lots of combinations, but you want to use these numbers that we just came up with, these perfect square numbers. So it looks like, in this case, 9 times 5 is a good choice. 9 is a perfect square number, so 9 would come out as 3, and we'd still have the square root of 5 remaining. Do another one. 8. It's not that big, so you can't go very far. 8 is the 4, so we'd say 4 times 2, but 4 is the square root. Perfect square number, it would come out as a 2. Go to 75. Break 75 down. Again, you go down the list. You're looking for the biggest number that you can find in your list here that goes into 75 evenly. So in this case, 25. 25 times 3. 25 comes out as a perfect square root number of 5, and that leaves us a 3 left over. So our final answer is 5 root 3. So that's called simplifying radicals. You've done a little of that in Algebra 1. We need to get better at it, and we will. And that's what part of our work is. And I've got some more work for you when you come to class. But working on absolute values, square roots, and how to graph quadratics. So bring any questions you have to class.